Hello everybody, my name is Megha Suswaram. I'm from University of California, Merced. I'll be talking about acoustic signal evolution under the trade-off between reproduction and starvation. Acoustic signal is exhibited by a variety of organisms including insects, amphibians, marine animals, birds, and mammals. Acoustic signal can be used for mate attraction, for reproduction, for alerting other members about potential predators, to exhibit food foraging places, and variety other reasons. I'll be looking at acoustic communication with a model organism, crickets. There are pros and cons of acoustic communication, advantages being they're not limited by environmental barriers, they're effective over distances and around corners, they're highly variable, they have fast change, and they encode high information content. Disadvantages may be they reveal the location of the sender to a potential predator. They're less effective in noisy environments, example seashores and highways. They may be metabolically expensive to produce, and they have high attenuation. Intensity rapidly falls with distance from the location. Acoustic communication in crickets are exhibited through chirps. There is a chirp period, there's a chirp duration indicated by the diagram, and within a chirp there are syllables, and there are syllable rates within a chirp. The bottom picture depicts the syllable rates and the chirp durations of various different field crickets with their frequencies over time. The acoustic signal is enough to attract females in crickets. This was tested by different experiments where they played the male's call over the speaker, and these acoustic cues were sufficient for the females to move towards the speaker and show phonotaxis. There have been many studies that look at the oxygen consumption versus the calling rate, that is the energetics in crickets and in amphibians. It is seen that within a single species of bush crickets, the calling rate is linearly corresponding with the oxygen consumption. The higher the calling rate, the higher the oxygen consumption within the individual. And this allometrically scales with different syllable rates for different insects and bullfrogs. I want to ask the question, under the trade-off between reproduction and starvation, does the signal evolve to be audible or silent? How does it influence the population dynamics? And could we qualitatively predict the likelihood of speciation? I built a model which has two components of fitness, a reproduction component of fitness and a mortality due to starvation component of fitness. In the reproductive component of fitness, I have Z, which indicates the syllable rate, and Z bar is the average mean syllable rate of the population, which we can consider as the ambient noise produced by the population. And we have R min, which is the number of individuals a signaler can mate just with movement without signaling. And we have R max, that is the maximum number of individuals a signaler can mate with, no matter what the highest syllable rate is. And this is with a model of a sigmoid curve that we have modeled the reproductive component of fitness. I also have the mortality due to starvation component of fitness, in which I have delta min and delta max. Delta min is the minimum per capita intrinsic mortality of an individual by natural factors without signaling, such as age and disease. And delta max is the maximum per capita mortality rate, and I have a model to produce the delta max. We are modeling this with a type 2 function. And then we use these reproductive components of fitness and the mortality due to starvation component of fitness, and we generate the fitness per generation of an individual as a function of the intrinsic reproductive rate times the logistic growth minus the mortality due to starvation. There are two approaches to solve these equations. I can either take the ordinary differential equation approach, in which I have to estimate the expectations, which may not be accurate, but it gives us an insight into analytical solutions. But whereas I do a full individual based model simulation, it has no analytical insight, but I can keep track of phenotypic variability. I don't have to estimate expectations, and I can keep track of all individuals. The energy reserve I calculate as the energy that the individual gains from the environment, and I subtract the resting metabolic energy of the individual and the consumption for signaling, the energy that is used for consumption for signaling by that individual. So I can model that with the equation x of t plus 1 is equal to x of t minus b minus s plus g, where x of t is the energy reserve at the parent time step plus the energy gained from the randomly varying environment, with mu as the environmental richness and sigma as the spatial or temporal heterogeneity. And I subtract the resting metabolic energy and the energy that is used for signaling. This gives us the delta max. I simulated the population growth and change in the mean syllable rate using MATLAB. I assumed a distribution of syllable rates from 0 to 100 units in time. I started with 1,000 individuals, which were distributed normally around a mean syllable rate of 50 units in time and a variance of 10 units in time. And I updated the population size with the mean trait value for 1,000 time steps. The distribution of population I plotted for different values of Rmin. The increase in mobility of individuals is what Rmin indicates. With the increase in movement of individuals, there was a decrease in reproductive incentive for signaling. There was transient arise in bimodality with a decrease in reproductive incentive, and evolution towards inaudible individuals with decreasing reproductive incentive for signaling. There was a sharp transition between audible and inaudible syllable rates. When there is no reproductive incentive, the crickets became silent, that is, when the syllable rate was either 0 or very low. They invest their time in foraging instead, and that decreases the mortality due to starvation. The crickets either evolve to become completely silent or maximize the syllable rate to the highest extent, and they become very audible. We can see a very sharp or quick transition between audible and inaudible values. The individual's mobility has an inverse relationship with signaling, that is, when there is increased mobility, there is decreased signaling. Increase in reproductive incentive for signaling, there is an evolution towards higher syllable rates, so there are loud individuals and a loud population. When there is decrease in reproductive signaling, incentive for signaling, there's evolution towards lower syllable rates, that is, there are silent individuals and silent population. When there is higher population densities for silent populations, there is no effort in signaling, as energy reserves are not depleted due to starvation. There's also a direct relationship between fitness and signaling, that is, when there is increased fitness, there is increased signaling. When the peak fitness of silent individuals is low and the peak fitness of loud individuals is high, the population evolves towards a loud population and the population thrives. When the peak fitness of silent individuals is high and the peak fitness of loud individuals is also high, then the population also evolves, but it evolves to be silent and it thrives. When the peak fitness of silent individuals and the loud individuals both are low, the population evolves to be loud, but it's not as dense, it's less dense. There's fitness benefits for silence. We say that silence saves energy. When the crickets evolve to become silent, they invest their time in foraging instead of signaling. The population sizes stabilize at higher values as there is no cost of producing signals, and there is minimum risk of starvation-induced mortality. We also saw that signaling impacts survival in different habitats, that is, less signaling helps survival. If individuals within populations start with high syllable rates, that is, if they're spending more of their energy reserves in signaling, then the model predicts that high mortality rates are seen, that is, high delta max. We can estimate starvation due to mortality by simulating different initial signaling energy consumption of individuals. Evidence of disruptive selection. In our model, individuals are always interacting and reproducing. There is no scope for speciation dynamics. We can continuously observe the appearance and the maintenance of traits for every individual within a population. There's transient arise of bimodality. What could be the causes? The cause is there are benefits to both increased signaling and to silence, so the trait is pulled in both directions. Here is an example of the transient arise in bimodality before the individuals move towards a silent population. There's likelihood of disruptive selection. In this graph, 0 indicates no arise of transient bimodality, and 1 indicates transient arise of bimodality before the individual evolves to become silent. Likelihood of a disruptive selection event with further conditions could be possible when there is bimodality, and these conditions could be environmental, genetic, or mating pressures like assortative mating. There's empirical evidence for supporting the results of our model. That is, there is a study done by Wagner, William, and Hoback in 1999 which shows that higher nutrition feeding groups showed higher chirp rates. There's also empirical evidence in the field cricket Requina verticalis that calling with relatively slow syllable rates may reduce the total cost of calling, and this may be a compensatory mechanism for their other high energetic costs of mating. There's also evidence that suggests that advertisement calls are produced aerobically and the aerobic costs are similar or exceed the aerobic costs of terrestrial locomotion. And there has been evidence of direction selection on Kauai for males to increase their mobility to compensate for their lack of song, and they're increasing their chance of encountering receptive females. We also look at empirical evidence for one of the assumptions of our model, which is alpha, which controls the sensitivity of the change in syllable rate to the mean syllable rate. That is, males have high mating success in low density. The conclusion of this study is that this model can predict the direction of acoustic signal evolution based on movement, resting metabolic energy, which is a function of body size, current signaling rate, and environmental richness. The richer the environment, the higher the investment in signaling. Signal is reduced when the risk of starvation increases. Increased movement of individuals causes reduced incentive for signaling, and this evolves to become silent. High signal energy consumption rates can lead to higher mortality rates in individuals. Population densities thrive in both silent and loud strategies and is dependent on individual movement, whether it's either silent or loud. Thank you. If you do have any questions, please write to me at msuswaram@ucmerced.edu.